Hi, we're going to continue our section on logarithmic functions. So we'll start with another example using those elementary properties of logarithms. We're going to solve an elementary logarithmic equation by turning it into an exponential expression. So if we had log base 3 of 2x minus 5 equals 4, let's rewrite this in an exponential expression. Take the base of the logarithm, 3. Remember, what your logarithm is equal to is the exponent, so 4 is the exponent. And what you're taking the logarithm of, that 2x minus 5, is the result of taking a to the y. So we have 3 to the 4th is equal to 2x minus 5. 3 to the 4th power is 81. Add 5 to both sides, divide by 2, and we get x is equal to 43. Now, one of the things that we talked about in the last video was the fact that you had two logarithmic buttons on your calculator, the common log and the natural log. That's base 10 and base e. We don't have a way that we could put log base 2 or log base 3 or log base 7 into our calculator. So we have this theorem that tells us that we can. What we can do is if a and b are positive real numbers and they're not equal to 1, and x is a positive real number, we can rewrite log base a of x in terms of any other base. So we could take log base a and rewrite it in terms of base b, where you take log base b of what you were taking the logarithm of, divided by log base b of the original base. And so you can do this for any base, including base 10 and base e, your common log and your natural log. So to turn it into a common log, it'd be the log of what you were taking the logarithm of, the log of x, divided by the log of the original base a. Or for natural log, it would be natural log of x over natural log of a. So where is this useful? If we wanted to evaluate log base 2 of 7. So in other words, we want to know 2 to what power gives you exactly 7. We're looking for that exponent. So the problem again is that we don't have a log base 2 button on our calculator. So we can turn it into common logs or natural logs, and you'll see it doesn't matter which one. If we wanted to turn it into common logs, then we would do log of 7 over log of 2. Put that in your calculator, you get approximately 2.8074. Or we could turn it into natural logs. Log base 2 of 7 would be the natural log of 7 divided by the natural log of the original base 2. Again, put that in your calculator and you'll notice you get the same 2.8074. You can do a quick check too, because that's the exponent. 2 raised to the 2.8074 gives you approximately 7.00022. Now it doesn't give you exactly 7 because we rounded these answers, so this is going to be a decimal approximation. Now here are some other properties of logarithms that are very, very important when you get into calculus. The first one is that if you're taking the logarithm, log base a, of two things being multiplied, you can break it up into two separate logarithms, the logarithm of the first plus the logarithm of the second. And since our other two special logarithms are written differently, I wrote the property out for those. The common log, log of m times n, would be log of m plus log of n. And the natural log of m times n would be the natural log of m plus the natural log of n. For example, if you had log base 4 of the quantity 3x minus 7 times the quantity x squared plus 11, you're taking the logarithm of two things being multiplied. You can break that up into two logarithms, the log base 4 of 3x plus 7 plus the log base 4 of x squared plus 11. Our second property says if you take the log base a of two things being divided, you can break that up into two logarithms, the logarithm of the numerator minus the logarithm of the denominator. It works for the common log, the log of m over n would be the log of m minus the log of n, and it works for the natural log. The natural log of m divided by n would be the natural log of the numerator minus the natural log of the denominator. For example, if we had the common log, log of 4x minus 3 over 7 minus x, we could break that up into two logarithms, the logarithm of the numerator, log of 4x minus 3, minus the log of the denominator, the log of 7 minus x. And the last property is if what you're taking the logarithm of is all being raised to a power, you can bring that power out front and make it a coefficient. That works for the common log and the natural log. The important thing about this property is that the entire thing that you're taking the logarithm of all has to be being raised to that power. So for example, if we had the natural log of the square root of x, as you can see here, nothing's being raised to a power, so this property doesn't appear to apply. But we don't have any properties for radicals, so we turn radicals into rational exponents. That's the natural log of x to the 1/2. Now, what you're taking the logarithm of is being raised to a power. You can bring that power out front and make it a coefficient. So now let's put these three properties to use by taking this example here. What if you knew that the natural log of 2 was about 0.6931 and that the natural log of 3 was about 1.0986? Let's approximate the following. What's the natural log of 39 over 81? Pretend like you don't have a calculator and you can't just plug it in. So what we'll have to do is evaluate this by breaking it up into as many logarithms as we can. We need to rewrite in terms of natural log of 2 and natural log of 3. Well, we are taking the natural log of two things being divided. That second property says it's the natural log of the numerator minus the natural log of the denominator. Now, is there a way to write 32 in terms of 2 and a way to write 81 in terms of 3? Yes. 32 is 2 to the 5th, and 81 is 3 to the 4th. Now, it's very important that you realize here that just the 2 is being raised to the 5th power, not the natural log of 2, so you can't do a substitution yet. But that third property says if what you're taking the natural log of is being raised to a power, you can bring that power out front. And so now we have 5 times the natural log of 2, which we know is approximately 0.6931, minus 4 times the natural log of 3, which we know is approximately 1.0986. So we plug those in, and we get that the natural log of 32 over 81 is approximately 0.9289. Now, if you plug this into your calculator and get the actual answer, you'll see they're actually very close. Now, we've done a similar problem to this, where we find the exact value without using a calculator, and I'm going to show you how the properties apply in this one. Log base 3 of 81 to the 5th. What you're taking the logarithm of is being raised to a power, so we can bring that power out front. Make it a coefficient. Now we have log base 3 of 81. Remember what we said before, if we could make the bases match, then they would cancel. So can we write 81 so it's an exponential expression as base 3? Yes, that's 3 to the 4th. So one of the properties we said if these match, they cancel and we're just left with the 4. Or you can use the property that we just talked about. What you're taking the logarithm of is being raised to a power, bring that power out front. And now we have an elementary property that says log base 3 of 3 is 1. So multiply it all together and you get 20. And we didn't have to use a calculator to do that. The last example we're going to go over using these properties is expanding into as many logarithms as possible. This is what's going to be very useful and very helpful for you in calculus. So for example, if we had log of the cube root of 7x squared, we want to rewrite this in as many logarithms as we possibly can. The first thing we need to do is get rid of any radicals by rewriting it as a fraction exponent. Now, that third property said what you're taking the logarithm of is all being raised to a power. Bring that power out front. So now we have 1/3 the log of 7x squared. We're taking the logarithm of two things being multiplied, so we can break it up into the log of the first plus the log of the second. But that 1/3 we'll need to distribute to both. Now here, what you're taking the logarithm of is being raised to a power. You can bring that power out front. And so this is the expanded form of that original logarithm. 1/3 the log of 7 plus 2/3 the log of x. When you get into calculus and you start taking the derivatives of logarithmic functions, being able to expand into as many logarithms is incredibly useful. The question always arises, how do you know that you've gone as far as you can? How do you know you can't go any further? You ask yourself 3 questions. Question 1, am I taking the logarithm of two things being multiplied? Question 2, am I taking the logarithm of two things being divided? Question 3, is what I'm taking the logarithm of all being raised to a power? And if you answered yes to any of those questions, then you need to use that property to expand. At the end, though, once you've asked those 3 questions and you answered no to all of them, then you know you're done. For example, here, am I taking the logarithm of two things being multiplied? No. Two things being divided? No. Is it all being raised to a power? No. So this one is done. Here, log of x. Am I taking the logarithm of two things being multiplied? No. Divided? No. All to a power? No. So that's how you know you're done. And again, being able to expand into as many logarithms as you can is incredibly useful in calculus. So let's do one more example. the natural log of x to the fourth times the square root of y cubed z to the fifth all over w. Remember, the first thing you need to do is get rid of any radicals. So we'll raise it to the 1/2 power. Now simplify whenever possible. Power of a power, there's not addition or subtraction in the parentheses, you can distribute that exponent. So now we ask ourselves these questions. Am I taking the logarithm of two things being multiplied? Yep, 1, 2, 3 things being multiplied. Being divided? Yep, we have things being divided. And all to a power, we do have exponents. So we are going to use these properties to expand. So the first one we're going to use is the division property. We were taking the logarithm of two things being divided. So we take the logarithm of the numerator minus the logarithm of the denominator. The question arises, how do we know we were going to use that property to start? Well, back up a step. If you find yourself asking where does something go, then that's probably not the property to start with. If you were going to use the multiplication property, you'd ask yourself, where does the w go? If you were going to try to use the property of the exponents, well, they're not all being raised to the same power, so you can't use that. So now you can see that we're taking the logarithm of things being multiplied. They are being raised to a power, but again, they're not all being raised to the same power, so we can't bring those exponents out yet. So we can break it up into the natural log of the first plus the natural log of the second plus the natural log of the third. And then we take that natural log of w being subtracted at the end. Now take a look. What you're taking the logarithm of is being raised to a power. You can bring those exponents out front. And so the full expanded version of this logarithm is 4 times the natural log of x plus 3/2 the natural log of y plus 5/2 the natural log of z minus the natural log of w. You are no longer taking the logarithm of things being multiplied, divided, or all to a power, so that's how you know you're done. Okay, we'll do some more examples of expanding the next time I see you.